Swayam Prabha. Digital India. Educated India.
So we are talking about Markov process and a consistency test for a Markov process, and then the transition probability that describes the Markov process. Okay, these are the context that we discussed so far, and now I want to go a little bit deeper and then explain that there are different kinds of Markov process also, and these kinds we distinguish based on how this stochastic process, the Markov process, varies in time. Is it continuous or is it discontinuous, and so on. Okay, so based on the trajectory or the sample path of a Markov process, we can distinguish into continuous and jump. And why we need to classify them is because the governing equations for developing these Markov process are a little different. Okay, so we kind of classify them into continuous and discontinuous, continuous and jump, and then look at respective governing equations. Okay, so to highlight this point, if you can think about two Markov processes. So as a function of time, so let's say that one particular process seen to vary like this. Okay, so we call this as W of t. Okay, so you can see that the path is irregular. You see some small jumps happening. Okay, and then there is another process which goes something like this. So if you look at these natures, okay, you see that this white trajectory, so let's call this as x of t. Both of these processes are Markov processes. Okay, what I am showing here is as a function of time how this process evolved. Okay, on one hand we see this Wt, which is irregular, and there are some small jumps, and then it goes like this. The other process x of t also has a similar character, but then time to time there is a big jump happening between states. Okay, now these jumps are much bigger compared to the local jumps that's happening in Wt. Okay, we say that these kind of processes are continuous. Okay, we call this as a continuous Markov process. This one we say as a jump Markov process. Jump or discrete or discontinuous. So we would like to distinguish between two kinds of Markov process. One where the jumps are very small. When we say small with respect to what? Suppose if you take any particular jump, the increment in that jump is not very different from its local average. Whereas if you look at these jumps, the extent by which these jumps are made are far higher than the average fluctuation about this point. Okay, so by looking at this relative increment due to these jumps, we distinguish between a continuous Markov process and a jump Markov process. Again, from a deterministic point of view, we think about continuity or a continuous function as something that is smooth. Okay, so you would think about some equation, something like an evolution, something like this. Okay, where there is no irregularity, it is a smooth function, it is differentiable. This is something we will see in deterministic framework. Whereas in the stochastic framework, you are going to see fluctuation about this, just like here. Okay, but these fluctuations are small enough compared to any local averages. Whereas in the case of jump processes, these jumps are much bigger, much larger. So therefore, we would like to classify the entire Markov process into two sets, one that is continuous, another one that is jump. So where do we see this kind of processes. Okay, for example, if I have a gas and then I am looking at the molecular velocity of these molecules, and if I make a plot of molecular velocity as a function of time, you are likely to see this kind of continuous variation about some mean value. Okay. On the other hand, if you think about molecules as hard spheres, okay, and these hard spheres are actually moving about, colliding with each other, exchanging momentum. In this picture of hard sphere collision, you will see the velocities are not continuous. It is going to take jumps. In fact, it is going to be a flat, and then there is jump whenever there is a collision happening. Okay, so the velocity can be continuous in some case. It can be also discontinuous in other case. It all depends on how we are describing the system. In a realistic case where molecules undergo collision, exchange momentum, in this case the collisions are not instantaneous. They take finite time. Okay, and because of this, the change in the velocity that you see are not like jump, they are kind of continuous. Whereas on the other hand, if you think of these molecules as hard spheres, hard balls hitting each other like a billiard ball, then the collisions are instantaneous, and the change in the velocity before and after are jump processes. Okay, you will see something like this. Similarly, you can think of any other process that you want to model and then see what is the nature of the trajectory is going to be based on how you are going to model it. So in this example I just now mentioned, I am still talking about velocity, but in one hand I am talking about velocity where the collisions are finite timed and then the changes are small. In the other case, I have an entirely different model system where the collisions are instantaneous, momentum changes are instantaneous, velocity changes are jumpy. Okay, same process, different way of modeling it, gives two different way of characterizing the system. Okay, so therefore when you think about a model, when you try to model a physical system, we have to frame ourselves that what nature of physics that is going into this picture, and then therefore classify whether we are talking about a continuous or a discontinuous Markov process. Okay, so now what we can do is actually we can give a mathematical condition for a continuous Markov process. So this is called Lindeberg condition. So in the limit delta t goes to 0, so we use this condition to say whether a particular transition probability for a Markov process is continuous or discontinuous. Okay. So what we are saying is, if you look at this, this is the conditional probability or transition probability, given that the system at time t is at z, okay, and then you are taking a step change in time, you are going to t plus delta t, okay, and then this random variable become from z to x. Okay, so that means you are at time t and then you are going to time t plus delta t. Okay, and then you are starting from z and then you are going to, let's say, x, right? Then what we are saying is that there is some small epsilon such a way that in the time interval from t to t plus delta t, the probability that this x will be away from z by some finite quantity that probability we are saying is going to 0, is going to vanish. Okay, that means this x has to be lying very close to z. It cannot go far away from z. If this condition is met, then we say this transition probability describes a continuous Markov process. If this condition is not satisfied, it means the x here at a small time interval can go anywhere outside this domain, so that the jump is larger. Okay, so that's what this condition means. Let me repeat one more time. What we are saying is that the probability that the state x will be away from x over a small time period delta t by an extent more than sigma, that probability is 0. Okay, in other words, in corollary, what we can say is that over a period of delta t, the next variable x is going to be in the neighborhood of z itself. It's not going to be far. It's not going to be far away from the variable z here. If this condition is violated, then we say that this is a discontinuous process. So I can give one example where it satisfies and another example where it does not satisfy. Suppose if I have x t plus delta t So this is a transition probability to describe a Brownian motion, the position of a Brownian particle. Okay. So if the Brownian particle is at z at time t, the probability at time t plus delta t, it will reach another place x is given by this normal random variable. Okay. Now if I substitute this equation in this condition, and this will satisfy. Okay, and that's what we are talking about here. This curve that I have drawn here is basically a Brownian particle's position evolving in time. Okay, and this evolution is predicted from this transition probability. Okay, the way we would have generated this trajectory is that we start from at some initial point z, choose a delta t, and then use that transition probability to get the next value of x, and that could have been somewhere here. And then you choose another delta t, again go to the distribution function, make the next next position, and then by doing this recursively, you will actually get this trajectory. And this trajectory follows this condition, Lenderberg condition, and we say this is a continuous Markov process. And if you want to write this little better, you can actually say this is x minus z is equal to minus epsilon to x minus z equal to plus epsilon. Okay, this is what it means. Okay, this is the interval with which we are calculating this probability. No, this is little, I think this is not correct. This should be away from this. So we want x minus z should be less than minus epsilon, and x minus z has to be more than epsilon. Is that correct? Now the second example is suppose if I have P11 x of t plus delta t given zt So this is a Cauchy distribution, and if I use this transition probability in this condition, you will see that this is violated. Okay, so that means this process cannot describe a continuous Markov process. It models a discontinuous Markov process. In fact, this trajectory I have shown here is actually a Cauchy process. The fact that you are getting this large jump is because if you plot the function, it has a very long tail. There is a finite probability of getting a longer time step once in a while. So those are these jumps that you see here. Okay, so this satisfies continuity condition, and this one does not satisfy. So having discussed about these two different sample path, continuous and discontinuous, our next objective is to come up with a differential equation, and this is basically called differential form of the Chapman-Kolmogorov equation. Okay, and why we need that? Because if I have a differential form of the Chapman-Kolmogorov equation, the solution of that will be the transition probabilities. Like I said before, without constructing the model, without solving them, we were talking about solutions and the properties of solutions. So now we are asking, where did this solution come from? Okay, so we are going to taking a step back. We are going to look at some governing equations whose solution will be these transition probabilities. Okay, so we are kind of coming other way around. Generally what we do, we have a physical process, we construct a model which can be a differential equation or a partial differential equation, then we solve, we get a solution, then we study the properties of those solutions. That's how we generally think. But here what we have done is, we take the form of a solution and we say that these are characterizing Markov process. Okay, those are the solutions, and we look at whether they're continuous, whether they jump, whether they follow Markov property or not, etc., etc. So having understood all these things, now we are taking a step back, asking where did these solutions come from? What are those governing equations? And how are those governing equations different when I have a continuous process or a discontinuous process? Okay, so those are the next questions. What I'm going to show here, I'll give the governing equation directly, but the detailed solutions are shared with my class notes. Okay, you can go through the proof. I mean, the derivation is not so important, but if you're curious, if you want to know, you can refer to my notes. So we are seeking a governing equation for transition probability of a Markov process general case. When I say general case, it can have both continuous and discontinuous paths within. Okay, that means if you have let's say two variable to describe a system, one of them can be continuous, another can be discontinuous. Okay. Since this is an important equation, I use a different color. Okay, so if you recollect, we talked about this Chapman-Kolmogorov equation of this form. This is what we said as a Chapman-Kolmogorov equation. When you want to go from x1 to x3, from t1 to t3, it can go via any of the intermediate states, x2, t2. Okay, so that's why we are doing integral over all possible x2. So we are going from x1 to x2, and then from x2 to x3, and then this is summed over all possible x2. This is what we defined as a Chapman-Kolmogorov equation. Okay, this we call it as an integral form. Now what I have done is, through some algebraic maneuver, we have changed this equation into a differential form. Okay, when you go from here to here, then you get this, what is called this differential Chapman-Kolmogorov equations. Okay, so if you look at this, on the left hand side, we are talking about a conditional probability that at time t prime, the system was at y. Y can be a vector, it can have multiple components, and then we are asking, condition to this state at time t larger than t prime, what is the probability that the state will go to z? Now we are talking about the rate of change of this probability with respect to time. Okay, the p alone is a conditional probability, but here we are writing on the left hand side, what is the rate of change of this transition probability? Okay, and that has some 3 components here. Now before I discuss what this means, let us define some characteristic equations. Okay, you will see that in these equations we are using this w's, a and b. Okay, so w happens here, occurs here, and this characteristic function a and b are also used. So what this means, if you look at the first one, these are called the jump probabilities. Okay, so what are we saying here is that if you look at the wx times delta t, this tells you the probability, the w times delta t tells you it's a probability that a system starting at z at time t will make a jump to x such a way that the x will be far away from z. So it's a finite jump. So that's why we've given a condition that x minus z has to be larger than or equal to some threshold value of epsilon. So here we are talking about the probability that over a time delta t, the system will make a jump to a larger extent, more than this epsilon. Okay, so that's, this condition basically means the new state differs from the old state by a finite amount, and the probability of happening this over a period of time delta t is this. Okay, in other words, w basically tells you the rate of change of probability to jump. It's called jump probability. Okay, the rate of jump, it's like a kinetic constant. Now if you come to the second one, here we are changing the conditions. So here we are saying the jump has to be larger than some epsilon. For defining a and b, I am making the other way around. I am saying that this jump has to be very local, because I am talking about a continuous process. For a continuous process, the new state has to be within the neighborhood of the old state by some small amount epsilon. That's why the magnitude of the change has to be smaller than some infinitesimal value of epsilon. In this condition, this a times delta t, this gives me the probability of the mean value of the displacement. Suppose if x, z, if they are all coordinates, if they are all positions of a Brownian particle, then this a times delta t tells you the mean change in the position, rate of change of mean. So this is the first moment of displacement. And similarly, when I go to this b of z comma d delta t, this basically gives me the second moment of the displacement. Again, I am talking about the displacement in the continuous limit. The displacements are happening locally. Then what is the mean, how the mean displacement changes with the unit time, and how the mean square of the displacement, how the second moment of that displacement changes with the time. Those are characterized by these equations. Okay. So now we take these definitions, and that's how these enter here. So by this, the first term that you see here, this characterizes or it captures the jump process through the characteristic function jump probability W. Whereas the second and third term, they comprise the continuity or the continuous Markov process, where this term associated with the drift kind of a behavior, and this one characterizes the diffusive kind of a character, okay, where the characteristic function A and B are defined by these equations. So when we try to set up a Markov process, the first challenge we face is how do we characterize those functions. This is where the modeling has to happen. Okay, you have to argue through, you have to look at the physics of the problem and then decide how you are going to assign an analytical function for W, A and B. These are all input functions. This will distinguish the physics of the problem. Okay, when you have a free Brownian particle under position, this is probably 0. This is probably also 0 because the mean position of a Brownian particle is 0, but this will be some constant which will be diffusivity. Imagine you have a Brownian particle confined to a harmonic potential we talked about in the case of Langevin equation. In that case, this will not be 0 because there is a force acting on it, the mean position is not 0, and this will be a constant diffusivity. So by looking at the physics of the problem, we will have to argue what is the nature of these functions are. Once we identify these functions, then we can take this entire equation and then apply boundary conditions and initial conditions and then go about solving them. So like I said before, the solutions are out there in the notes. The derivation of this expression is given in the notes. So now what I want to do is, we will take this general case and then break into simpler cases, asymptotic cases, which is more specific to a given condition. In this case, you will see that A and B, these are all 0. Okay. In the cases where there is no continuous variation in the process, only W is defined, W is finite, this is non-zero. Then we are talking about only this term. Okay. So we say that dou P by dou Z you have only this term, and this we call as a master equation. A master equation describes only the jump Markov process, where this y and x, they will shows this kind of a jumpy behavior. Now here we think y, z, all of them as a continuous variable, like a position of a Brownian particle or velocity of a Brownian particle, but we can also keep them as a discrete variable like number of molecules, number of electrons. Then we can write this equation in a discrete form. this equation is written for a continuous variables and this equation is written for discrete variable, where n, n prime, m, all of them are discrete variables. They carry integer values. The physical reasoning of this equation, what it basically means is that when you are trying to look at a condition, the state is at n prime and then you are looking at when the state will reach at n, it goes through many possible intermediate states m. Okay, so then this one tells you the rate of generation of this flux, and minus this tells you the rate of outgo from the current places. So in other words, let's say you have n prime here and n here. Okay, so you want to look at the probability of change from n prime to n, and this can happen from the state n to this and from here to here. Okay, so that's what these terms basically captures. This is state m. This is the probability that the state will be found here, and then it makes a jump by this rate to n, minus this one tells you that given that you are here and you reach there and also make a jump from here to some other intermediate states. So this is basically the net probability rate of change. Case 2 is a continuous Markov process where W is 0 and A and B, these are non-zero. When you have characteristic functions A and B non-zero but only W is 0, all the first term would have gone and then you are left with only this and this. Okay, have you seen this kind of equation before? In this form, you must have, you should have. Huh? Sorry? Navier-Stokes, no. It comes in one of the transport problem. I mean, it is called diffusion equation, right? In mass transfer and heat transfer, you should have studied heat transfer or mass transfer. So we call this as the diffusion equation, or also called the Fokker-Planck equation. In the diffusion equation, instead of P, we would have concentration or temperature. Okay, otherwise we have this kind of a partial differential equation of a second order. So we call this as a diffusion equation, or more generally Fokker-Planck equation. So Fokker-Planck equation or diffusion equation are good models for describing continuous Markov process, whereas the master equation that I talked about is only for jump or discontinuous process, and both can be shown as a limiting cases of more general differential Chapman-Kolmogorov equations. So we are talking about three equations. The more general form is the differential Chapman-Kolmogorov. For the discontinuous or jump Markov process, it's the master equation. For the continuous Markov process, we have diffusion or Fokker-Planck equation. And the third case you can think of as the one that has everything inbuilt. Okay, you have jump, you have continuous and all that. So suppose if you have a more general case, what you are likely to see is the following. I'll show one example of the so here W, A, B, they are all non-zeros. you will see something like this. What you see is that you see there is some sort of drift towards an increasing direction because A is positive, A is a drift. Okay, the mean is changing with respect to time. So you see some sort of a positive slope everywhere. You also see this larger jumps because of the finiteness of W. Because B is non-zero, there is going to be some sort of diffusive behavior also. There is going to be fluctuation about this. If B is 0, what would have happened is you will not see all this local fluctuation. You will see straight lines and then drops, straight lines, drops, and so on. The small jiggling that you see here is because of the finiteness of B. This tendency to increase at an average, the mean, that's because A is zero, A is non-zero, and W is non-zero, and you see that this kind of jumpy behavior. So here I have superimposed both the continuous and discontinuous process. Within the continuous process, I have a drift and I have a diffusion. All three things are actually clubbed together. Sorry? What is W? So W is the probability to jump from one state to the other. That characterizes the jump process. Like I was saying, the velocity undergoes a collision, and the velocity suddenly takes a different value from the previous, and that actually signifies as a bigger jump. So here I am showing some x, some random variable x, that shows some local variation and drift, also sudden jumps. Now, as a homework, you can think about different combinations. Okay, keep only W non-zero, A and B 0. Predict what kind of trajectory, what kind of sample path it would create, and keep only A and B non-zero, and keep W 0, and then expect what sort of sample path, and many other combinations. All right, okay, so we'll stop here.